So we agreed that today we're starting with we start with rational graphs. The question, sketch 1, f of x is equal to x plus 1 over 3 plus x. So whenever I'm asked to sketch a fraction, the first thing is to equate the denominator to 0 as we search for the vertical asymptote. So 3 plus x is equal to 0, so that x is equal to minus 3. The second thing, to find the horizontal asymptote, now that anyway, we have so many tools, but we still stick to the cheap one. You just check the powers. So you find the powers of x are equal up and down. So we are saying y is equal to 1 because it's 1 over 1 there. It's coming from the coefficient of x up and x down because the powers of x are equal. And then if I have those, I may want to find, of course, the y-intercept by taking 0 where there is x. So I have 0 plus 1 over 3 plus 0. That would be 1 over 3 y-intercept. The x-intercept always, please, always equate f to 0. Okay, so get the whole function x plus 1 over 3 plus x and equate it to 0. When you do that, you don't care about the denominator because we cross multiply. So multiply, we have x plus 1 is equal to 0. So that x is equal to minus 1. So now I have everything I need. I can graph. So first, x is equal to minus 3 is the vertical asymptote. Y is equal to 1 is the horizontal asymptote. Then I need to graph on the left and on the right of the vertical asymptote. Up and below the horizontal asymptote. So on the right, that's where we have the intercept. So we have the y-intercept at 1 over 3 here. The x-intercept at -1. So the graph here is going to come like that. Crossing at -1. Okay. Then we pick a number that is less than -3, say -4, and substitute in the function. We are doing this so we can know where to put the graph. Is it above the horizontal or below on the left hand side of the vertical asymptote? So we're going to have -3 over -1, which is +3. +3 is above 1. So we put a sketch here. Like that. Okay. Please don't forget. Step 1. Find the vertical asymptote. How equate denominator with 0. Okay. Step 2. Find horizontal asymptote. How take the power of it. And then step 3. Solve fx is equal to 0, we find x intercept. In step 4, substitute x is equal to 0. In f, we find y intercept. Okay, so the -4 was just picked at random in trying to see where we should sketch in this region. Is it up here or it's below? Was needed to put a graph here. So we pick a number that lies in this interval. So since this is -3, -4 is somewhere here. So we could have picked -10, any number less than -3. Then it would have helped us to know where the graph is going to be. So you only follow those 4 steps I've put there. The first thing, find the vertical asymptote, find the horizontal. So for f equal to 0 to find the x-intercept, and then substitute x0 in f to find the y-intercept. That should be enough for such kind of graphs. You don't expect much things. Now let me do one where you may have 2 vertical asymptotes. F of x is equal to x of x plus, or let's put x plus 2 over x squared minus 4. So I want to do that. Okay. So, step 1, vertical asymptote, x squared minus 4 equal to 0. So we get x squared is equal to 4 with square root. So we have x is equal to plus or minus 2. Okay. X is equal to plus or minus 2. That's step number 1. Step number 2, horizontal asymptote. So you check the power of the numerator is less than the power of the denominator. So y is equal to 0 there. Step number 3. Those we can interchange, but then we're going to start to do them the way we order them. So we put x plus 2 over x squared minus 4 is 0. So we have this, meaning x is equal to minus 2. Like that. Okay. Okay. The fourth part, you substitute 0 while there's x. So we get 0 plus 2 over 0 minus 4, which is 2 over minus 4, which is negative half. Like that. Then now we draw the graph. So we're saying the asymptote here is 0 and what? Plus or minus 2. Minus 2 plus 2. So we have minus 2 positive 2, 0. When there is x in the numerator, so to avoid messing up, let's make this number here be 3. Otherwise, so many things will be messed up there. And we make it positive 3 there, so that we have a 3 like that. So we'll have a 3 over negative 4. And here we'll have x is equal to minus 3. So 3, 3. So here's what you do. So I've changed it to 3 so that we don't have anything canceling there. I think then I'll need to put another example where the things can be cancelled, and then we'll see how we approach it. Of course, that one I'll use it much on the limit part. So you have this, and you have identified that the y and the x axis is the is the horizontal asymptote. But if, so take note, if there is x in the numerator and the horizontal asymptote, if there is x in the numerator and the horizontal asymptote is 0, equate the numerator to 0, for this case, the horizontal asymptote is what? Okay, so this case, the horizontal asymptote is cut. So you have cross the horizontal asymptote. Normally, you don't touch the asymptote. But for this case, it is stacked. So what will happen is, at x is equal to minus 3 here, the graph is going to cut that asymptote. So we check what happens when x is equal to, say, minus 4. So what will be f of minus 4? We want to see where it's coming from. So f of minus 4 is going to be minus 4 plus 3 over 16 minus 4. This is minus 1 over 12. So it's coming from down. Okay, so meaning that it's negative, so meaning that this is going to be a graph of this kind. And then we have found what? We found the x-intercept. I mean, the y-intercept would be minus 3 over 4. So minus 3 over 4. Okay. So it means that the graph is not cutting the x-axis anywhere else. So since we have the equal space -2 to 0 and 0 to 2, so we make this a turning point inside there. And then we pick a value on the right of 2. Say we pick +3. If we pick +3, we are going to have 3 plus 3 over 9 minus 4. This is 6 over 5. So it's above the x-axis. So the graph is like that. Okay. So the graphs, when it comes to turning points, even the polynomial graph, I want you guys to be a bit careful when turning. Okay. Because I've seen you mostly turn on the y axis. You only turn on the y-axis if the spaces between your lines or between your intercepts are equal. The bigger space always takes the turning point. If they are equal, you have no option but to turn on the axis.
So, sir, you can't get the value that is between -2 and 0. Just testing. If you test, is it going to turn again, or maybe you just have no option than to turn?
So if you test, let's say we use 1. F of 1 is going to be 1 plus 3 over 1 minus 4. This is 4 over -3. So it's down. Okay. Then if we try f of -1, you get -1 plus 3 over 1 minus 4. That is 2 over -3. So they are negative for any number that we test. So the concept here is you may meet something that needs to be factorized before you can see the vertical simplex. Please feel free to factorize, have the simplex, and also going up. Okay. Let's go to the third example. F of x is equal to 1 plus x plus 3. So this is a radical graph. The graphs of radical functions. So if I have radical functions, I first go inside the root and equate to 0. So I'll get that. From there, I go back to f and substitute -3. What this means is that I'll get 1 because I'm making the inside 0 again. So I have 1 plus 0, which is just 1. So this point -3, 1 is the starting point of the graph. When I find that point, I can even go and click on the graph. So I have -3, 1. I put the point there. So if what I have here is positive, then I know that my graph is going up. So there will be no x-intercept. Okay? There will be no x-intercept. So there will only be a y-intercept where I substitute a 0 now while it's x. So I have 1 plus the root of 0 plus 3, which is equal to 1 plus the root of 3. So meaning I'll have a graph there. This is 1 plus 3, like that. Okay. So if you find that it's negative there, let me give you this one. F of x is equal to, we have 3 minus the root of 2x plus 5, for example. Because it's minus, when you sketch your graph, is going to face down. Yeah. The direction there is determined by other properties, but you know it's facing down. So we get 2x plus 5 and equal to 0. We have x is equal to minus 5 over 2. So it means that the starting point will be minus 5 over 2, comma 3, like that. And then so we have minus 5 over 2, comma 3. So it's starting from there and it's facing down. So I go inside and check my x. It's positive x. So it's facing down to the right. So we need to find the y-intercept. So when x is 0, we have 3 minus the root of 0 plus 5, which is equal to 3 minus root 5. This is a positive number. The graph is very positive like that. And this is 3 minus root 5. Root 5 is less than 3. Since 3 is the root of 9. So I need to find that x-intercept. Find x-intercept, you always equate f to 0. So we have 3 minus this equal to 0. So that's like the radical equation. So we take the root the other side. So square, so we have 9 is equal to 2x plus 5. This is 2x is equal to 4. Divide by 2, so x is equal to 2. So that is equal to 2. So you have your graph. So graphs, you need the x-intercept, you need the y-intercept. You need to know where it's starting from if it's radical. The same way we start a radical graph is the same way we start the modulus graph. I think you saw that in the book. And it's the same way the exponential graphs are also here. Like they always have that thing, that number, the y part. It's always seen, it's standing on its own. Okay, so what you're trying to say here is that when you go in the test, you may find so many graphs. Okay, we're expecting that there should be at least, depending on the coverage, there could be modulus graphs. Okay. There could be radical graphs. There could be rational. Okay. And there could be piecewise graphs. What else? There could be tree graphs. So we could have exponential graphs. We could have log graphs. So all these are within which, for the trig, we expect much sine or cosine. That's what we expect. So you have all those graphs there. And we did the modules, we did the radical, we did the rational, we did the piecewise, we did the trig, we did the exponential, we did the log. So now we'll do a graph. This was question 4. So question 5. Put it here. So we'll do a graph of this kind. Sketch f of x is equal to x minus 2 over x squared minus 4. If x is not equal to 2, and then maybe let's say 3 if x is equal to 2. So sketch and determine continuity at x is equal to 2. Okay, so let's get at the graph. So first we pick the upper part. F of x is equal to x squared, x minus 2 over x squared minus 4. So, if we substitute 2 at this point, this function is not defined. So let's try to simplify it a bit. We put it as x minus 2 over x minus 2 are x plus 2. So these can cancel, and so we have 1 over x plus 2. Okay, so that's what kind of a graph is that? It's a fraction. It's a rational graph. So it has the asymptote when x is equal to 2. So in this case, we'll just treat that asymptote as a whole. So we substitute 2, we'll get 2 plus 2, which is equal to 1 over 4. So at 2, 1 over 4, there's a whole there. Okay, so we'll treat it as a whole, which is actually an asymptote. And then we can now sketch our function. So that is when x is 0, we are getting 1 over 2. So we have 1 over 2 there. And also when x is, say, 3, what do we have? So we have 1 over 3 plus 2, which is equal to 1 over 5. And so because of the nature of the graph, this is the asymptote. So our graph will be the curve, not the line. It will be like that. So that's the kind of graph that we have.
Sir, I'm kind of asking if you can just run through. I didn't understand.
Okay. Maybe Let's do this. So we are saying this function is, it's f of x is equal to 1 over x plus 2. After we have worked on something there. Now here's what we obtain. This is a radical function. I mean, it's a rational function. So it has a vertical asymptote. X plus 2 is 0. So at x is equal to minus 2. Yeah, like this. Okay. Look at made on this thing. So at minus 2. But then it's also not defined. It's also not defined at 2. In the initial state, at 2,1 over 4, it's not defined. So that means that it also has the asymptote on the red line there. So it means that this side, our curve will be like this. Then we also need a curve on the other side. So let's pick, say, minus 3. So get 1 over minus 3 plus 2, which is 1 over negative 1, which is minus 1. Okay, so yeah, well, now it makes sense. So we have another curve inside. Okay, good.
Yes, sir. So I wanted to ask, is it okay to like find the vertical asymptote using just the original equation and then you solve later on?
Yeah, it's okay. You can find. Yeah, but because even here we're saying x is equal to 2 is an asymptote, except that on that curve there, it's an asymptote that you can cross. So that's why we don't treat it as an asymptote, because it's a cancelled asymptote. So we only respect it at x is equal to 2,1 over 4. So if the fractions are something that is cancelling, you don't treat them aside. You cancel before you can start making out the steps. So now, look, this thing was defined as when you get f at x is equal to 2, it's giving us 3. It's giving us 3. So it's open at 2,1 over 4, but it's closed at 2,3. Remember this was half. So now, if you want to check if it's continuous, the conditions are that f of 2 should be defined, and for sure, defined as 3. 2, you need to find the limit as x approaches 2. So if you check the limit as x approaches 2, we only have one piece where there is 2 there, which is this one. So substitute in 1 over x plus 2, and what we are getting is 1 over 4. So now, the limit as x approaches 2 of f of x is actually 1 over 4, which is not equal to 3. And 3 is f of 2. What does that mean? F is not continuous. At x is equal to 2. So this video will cut you very soon. Please wait for 10 minutes and join back. Thank you.